Okay, so this is our Screencastify video for lesson 1-2 for AB, functions and graph. Okay, and the first heading on the margin on page 12 is functions, and we're just pointing out to you that we don't really refer to the variables so much as x and y anymore. We refer to the input, the x, as the independent variable, and the output, the y, is the dependent variable. And f of x here is another way to describe y, the height of the graph. So if you have a function, each input, each independent value will map on only one dependent value. And you're familiar with the vertical line test, and that's the point. As you slide a vertical line along the x-axis, it's only going to hit the height. It's only going to hit one height. Okay, and if it hits more than one height, the graph fails the vertical line test, then it is not a function. On page 13, domains and ranges. So we're talking about this in terms of the independent variable, the domain for x. If x is between a and b, that is an open interval. Okay, a and b are not included. So in terms of a number line, you would have an open circle. And in terms of interval notation, a and b are enclosed by parentheses. If a is less than or equal to x, then x is larger, a is the left bound, but a is included. So a would get a bracket, and you would go to the right without bound, and parentheses always gets, infinity always gets parentheses. If b is greater than or equal to x, b is to the right of x, so your domain starts as far as left as you can go, which would be negative infinity, always gets parentheses in the interval notation, as far as b, bracket, because b is included. So the bottom two lines get closed circles on a number line, closed circle where there's a bracket, okay, and then open circles in the first example where you have the parentheses. So example 2, which is on page 14, you get a couple functions. The first one's 1 over x. So here's the graph of 1 over x. What do you notice? Well, x can't be 0. You can't put 0 as the input in the denominator. And then the height can't be 0, because the only way the only time y is equal to 0 is if 0 is in the numerator. And this is fixed at 1. So here's your graph. The domain is all reals except for 0. The range is all reals except for 0. We can abbreviate it. X can't be 0. Y cannot equal 0. All reals is implied. So for the other example, you have root x, and you can't take the square root of 0. So the domain includes 0. You can't take the square root of a negative. So you would be bracket, because 0 is included, to the right. Interval notation, 0 to infinity. Infinity always gets parentheses. The range, the square root of 0 is 0. So it can have a height of 0, but it can only have positive heights. So you have the same notation as you did for the domain. Okay? So we're going to ask you to pause the video and using this as your model, and you go to exercise 9 on page 19. So for number 9, what do you notice? Well, here's the problem you had. But if you relate it to the pre-image, what happened? X got replaced by x plus a negative 2. So it's the same problem you just did in example 2, but the graph has been shifted 2 to the right because you did the opposite and you replace x with x subtract 2. So I take the domain from the example we just did, and the range and shift them 2 to the right. So now the domain for this graph is x cannot equal 2, all reals except for that, and the range is not affected by a horizontal slide. Okay. The next heading in the text, even and odd functions. An even function has symmetry about the y-axis. The graph reflects onto the y-axis itself. So the most user-friendly example of an even function would be y equals x to an even exponent, x squared. But technically, the definition is f of negative x equals f of x, meaning if you go the same magnitude to the left, negative x, as you go to the right, the heights would be the same. So if I think about y equals x squared, if you go 2 to the left, the height would be 4. If you go 2 to the right, the height would be 4. That's an even function. For an odd function, if the input, if you go to the left, that would give you the opposite of what you got if you went to the right. And the symmetry of an odd function would be a rotation of 180 degrees. So the most user-friendly odd function would be the power function y equals x cubed. So if you go 1 to the right for x cubed, gives you a height of 1. If you go 1 to the left, negative 1 cubed gives you a height of negative 1. Okay. Piecewise functions. Okay, so example 5 in the book on page 16 gives you a piecewise function, which is, ready, negative x in quadrant 2. So here's the graph of y equals negative x. When x is less than 0, it's x squared at 0 and to 1. So this parabola is for the x squared component is for all points between and including 0, 1. And then it's the line y equals 1 when x is greater than 1. So don't really worry about the notation here about how this graph was drawn. You're not going to have to do that on the AP test. I think you're better off drawing the piecewise graphs by hand. So again, we're going to ask you to pause the video, go to problem 33 on page 19, and we will go over that with you. Now, I know I asked you to do this by hand, but if we do, ready, what have you had here? When x is less than 1, you've got 4 take away x squared, which is really y equals x squared is opening down and then been shifted up 4 until you get to 1. Then what? Then you have a linear equation, 3 halves x plus 3 halves between 1 and 3 inclusive. And then the slope changes to 1 from 3 halves to 1 when x is bigger than 3. So you have these 3 branches. Absolute value function. So the preimage is y equals the absolute value of x. Now what do we have here? We have the transformation. This is a slide of h units to the right up k, following a scale change of AB, where the A and the H affect the input, the B and the K affect the output. And you accomplish that by doing the opposite. So to expand my x's by a factor of A, I divide x by A. To expand my y's by a factor of B, I divide by B. And this is a slide. The open circle represents following. So you're doing the scale change first. Then to do the slide, you replace x with x take away h, and you replace y with y take away k. This is 100% correct. You can leave it in this form. This is just getting y by itself to this line, but this is fine. Okay? So in example 7, on page 17, they give you this. They want the domain and range. Okay? So we just back up and say, if this is the image, what's the magnitude of the transformation? Well, A and B are 1, which is the identity element of multiplication. So there was no scale change in this graph. It was slid 2 to the right, down 1. You replace x with x take away 2, which slides it 2 to the right. You replace y with y plus 1, which slides it down 1. So if this is the domain, all reals for the pre-image, and this is the range, greater than or equal to 0, then we just do that slide here. And what happens? The slide of 2 to the right does not affect the domain. But sliding the graph down 1 affects the range. So now the range of the image is y is greater than or equal to -1. And if you were to write that as an inequality, y is greater than or equal to -1, it's equally correct. Okay? So again, we're going to ask you to pause the video, use this as your model, and go to problem 49. So in 49, we have this graph. What happened in the graph? Well, the absolute values, you have the opposite of the absolute value. So the graph is inverted, it's opening down, and it's been slid 3 to the right, up 2. The domain isn't affected, but now the range becomes -infinity up to and including 2. And then example 8, composite functions, we have y1 is x squared, and in the book they refer to that as g, and f is x take away 7. So if we want to do composite functions on the calculator, we type vars, y-vars, function mode, and you type the outside function, which in this case, the textbooks ask you to do f following g. So g is the input. So you want f of g. Okay, so you would end up with x squared take away 7, if you did this algebraically, because this is the input. So you put the 2 in here, you get a 4. 4 plus a -7 is a -3. And that's what the calculator is giving you in Y3 if you ask it to do the function composition for you. And last time, we're going to ask you to go to problem 51, which is on page 20. So for 51, we're going to do this algebraically. Here's f and here's g. So A asks for f following g. So g is the input. So I take all of this and put it in here, and you have x squared take away 3 plus 5. Combine your like terms, x squared plus 2. B says g following f. So f becomes the input. When you do the input, you square it and then take 3 away. So with a lattice, I would get x squared plus 10x plus 25. Take away 3, x squared plus 10x plus 22. So for C, they want f following g of 0. So I can go up to A and put 0 in here. We get a 2, which is telling you put 0 in for G, and you would get -3. Put -3 in for F. -3 plus 5 is 2. G following F of 0. We go to B. Put a 0 in there, cover up method, and you would just get 22. E asks for G following G of -2. So we put -2 in for G. -2 squared is 4. Take away 3 is a 1. And make 1 the input. 1 squared is 1. Take away 3 is a -2. And for F, take away F. F following F. This becomes the input, and you would have X plus 5 as the input. What does F do to that? It adds 5 to it, and you would get X plus 10. So problem 51 is helpful to remind you of what you did in Algebra 2 with function composition. Okay? So that's all for 1, 2. 1, 3, we're going to pick up with the Zoom videotape from the fall of 2020, and then the videos are going to alternate between Zoom and Screencastify for Chapter 1. Thanks.